Now I want to look at limits of the form infinity minus infinity. And those infinities don't necessarily cancel, right? This first thing, it really depends who's growing faster or not. If they were both headed to infinity at the same rate, they could cancel off and be zero. But if, things can head off to infinity in much different fashions, as we've seen. So we want to try and take something like that and get it into a ratio so that we can use L'Hopital's rule. And depending on the stuff involved, you might use trig identities, you might use properties of logs, you might use some algebra. Somehow you want to rewrite it so you can get a fraction so that you can use L'Hopital's rule. So let's look at an example. Say we were taking the limit as x goes to infinity of square root of x plus 1 minus the square root of x. Now, square root function we know goes to infinity. So we are looking at, and this one's just shifted over a little bit from this one. So we are looking at a form of infinity minus infinity. And there's a pretty good hope that those are going to cancel, right? Because these aren't drastically different functions, right? They're both square root functions. One is just advanced one unit ahead of the other one. So we would probably guess that those are going to cancel, but we gotta see that happen rigorously. So the idea is, how can I get a fraction started? There's no fractions involved there. Well, when you have two things being subtracted, one thing that works out nice often, as we've seen in algebra, is multiplying by the conjugate, by the same expression but with addition there. And remember, you have to do the same thing on top and bottom, and that introduces a fraction there. So let's take our original expression, and we're really multiplying by a form of 1, right? By doing this, this is just something over itself, so it's 1. But the reason we pick that is that when you take a minus b times a plus b, you get a squared minus b squared. So it's going to simplify things down nice. It's going to get rid of square roots. So when you multiply those first two, you get x plus 1. When you multiply the middle ones and the outer ones, those cancel. And then square root of x times square root of x is x. Plus. But that's going to cancel. We just have 1 on top. And actually, this is really nice. In this case, we don't even need L'Hopital's once we've rewritten it. So this is really just a practice at algebraic manipulation. But because now look what you have. That's headed to infinity. That's headed to infinity. But now it's a sum of infinities. So they're both adding to each other. So that even more so goes to infinity. So you have a constant 1 over something headed to infinity. That limit is just 0. So luckily, we didn't even have to use L'Hopital's, but that is going to get you into a fraction. And in some cases, when you get to here, you'll have something that you may need to differentiate using L'Hopital's rule. And as we kind of suspected at the beginning, because these are similar functions, they're really the same function, just shifted, it's not surprising that out at infinity, I mean, think about this for really big numbers. Square root of 1,000,000 plus 1 versus square root of 1,000,000, those numbers are essentially the same. And that plus 1 becomes less and less of a difference as you get farther and farther out. And that's what we're seeing here with this limit.